here we are with another one of our video presentations. And this time our topic is universal gravitation. So the idea here starts with Newton seeing an apple fall out of a tree, or so the story goes. And the story says that Newton, seeing the apple falling out of a tree, realized that something made it fall out of the tree, and that same something was what kept the moon going around the Earth and the Earth going around the sun. And this is universal gravitation, the idea that there's an attraction between every two objects in the universe. So he again used this to explain lots of those things. All right, so here is the moon going around the Earth, and please note that is not to scale. But there's our moon going around the Earth. Okay. So let's talk about this. If there's an attraction between every two objects in the universe, what are the factors? What do you think the factors are? So you want to pause and think about it, that's okay. But let's see how you did here. Okay, well, the masses of the object are going to have something to do with it, and the distance between them. As the masses get larger, the attraction gets larger. And as the distance between them gets larger, the attraction gets smaller. Interesting. So let's talk about this equation, this Newton's law of gravitational equation. So there it is. F we're accustomed to as forces, m are masses, so this indicates the two masses, and r there indicates the center-to-center distance between them. They use the letter r because it could be a radius of a circle. The center-to-center distance could be anywhere around that circle. Interesting here that it is an inverse square relationship. So if the distance is doubled, the attraction becomes 1/4, not 1/2. This inverse square relationship shows up many times in physics. We'll see it again in electricity, and it also shows up in light intensity. Kind of interesting that this same relationship, this inverse square relationship, seems to keep coming back up in nature. So why that's true, we don't exactly know, but it seems to be a consistency. Very interesting. Some mysteries have not been solved, but that's interesting that that one keeps coming up. Interesting to me anyway. All right, G, the universal gravitational constant, will make sure that these masses and these radiuses multiplied together will come out to the force between them. This is a constant, unlike our small letter g, that's good anywhere in the universe. You know, small letter g is the acceleration due to gravity in a localized area. So here I'm putting the value for it. It's 6.67 times 10 to the negative 11th. I'm not putting the units there. Do you know what the units are going to be in order to make that come out to be a force in newtons? Well, there's a little challenge question for you that we can talk about in class. Okay, so here's an example. You're given two masses. They're going to be a distance of 20 meters apart, and I'd like you to calculate the force of attraction between them. I'll pause here, give you a chance to see if you can come up with the answer that I got. Okay, you're back. Let's see how you did. My answer was a very small force of attraction, 2.50 times 10 to the negative 11th. How did you do? Are we somewhat in agreement on that? Well, if you didn't get that answer, we could certainly talk about it in class. Okay, so there's a force of attraction between every two objects in the universe, so I should be noticing these forces all the time. I'm attracted to this napkin container, apparently. I'm attracted, apparently, to my iPhone. So why is it that I don't notice these attractions all that often? Why do you think that is? You can pause if you like. You can pause anytime you like, and maybe think about that. Okay. Did you do that? Did you give it some thought? All right. Well, one of the things is these are very small forces. And the other thing is there's a very big thing going on around us that really makes us feel the attraction, and all the other ones are small compared to it. So it has to be very close to you and very massive as well. Do you know something that's very close to us and very massive that would override all these small attractions? Well, the Earth. The Earth is something that we're definitely attracted to, and we can feel that force all the time. If you don't believe me, try jumping away from the Earth and see how fast you come crashing back. That force of attraction is always there. Okay, the Earth is close and very massive, of course. And this attraction that we feel to the Earth, or we would feel with the Moon if we were there, or on any other planet, is what we call our weight. And we've already been talking about weight as W is equal to mg, the localized acceleration due to gravity. So how about that, just for fun? Calculate the weight of a 65 kilogram object using W is equal to mg and see what you come out with. After a quick pause, you can come back, and now that you are back, you would have gotten an answer of 637 newtons. Now remember here, this is good on Earth at sea level when the acceleration due to gravity is 9.8 meters per second squared. But that's not the case everywhere in the universe, so this is good for on Earth. But let's use this in our new concept to talk about the idea of universal gravitation and how our force of attraction with the Earth is also the weight. So this time around, let's use the 65 kilograms as one mass, and the mass of the Earth, this is the actual mass of the Earth, or close to it anyway, as mass number 2. Now the radius of the Earth is also important, and remember that the value r is your center to center distance. So even if this 65 kilogram object is right on the surface of the Earth, we would be concerned with its distance back to the center of the Earth. And that's why the radius of the Earth is important. So go ahead and make that calculation, pause, come back, and we'll see how you did. All right, how did you do? You should have found an answer that was very close to the 637. So here's 636.94, that's what I got. Is that what you got? And you can see that these numbers work out very well. Now universal gravitation will let us figure out the force of attraction between any two objects anywhere in the universe. So let's try this one. Let's come up with a hypothetical planet with some hypothetical masses and figure out the weight that a 50 kilogram person would feel. Now if it was on Earth, you could just use W is equal to mg, but we don't know g on this planet, at least not yet. But we can figure that out. So here's a look at the planet, hypothetical planet. I don't know, that's some planet anyway. And why don't you pause and see what you come up with as that force of attraction. Okay, welcome back. Here's the answer that I got. This would be a very heavy planet, heavier, more gravity than our planet. So 1,740, something like that, newtons. Now, as a follow-up question, I'd like to get the acceleration due to gravity, the small letter g on that planet. All right, so that's my question. What is the acceleration due to gravity on this planet? Well, you just found the weight of that 50 kilogram person. You didn't find the weight of the planet, no, but you found the weight, W, let's say in the equation W is equal to mg, of that 50 kilogram person. So using the person's mass of 50 kilograms and that weight that we found, we can find out the acceleration due to gravity, which on that planet would be 34.8 meters per second squared. How did you do? All right. Well, if you have any questions, please bring them to class, and we can figure all of that out when we're together. Okay, let's see what else we got going. Here I have the Earth again. You'll remember, hopefully in your notes, or you can go back in the video, or actually I think I have it on the next screen, the values here. But this time the person is 270,000 meters above the surface of the Earth. So, in making this calculation, the R value would have to take into account the distance to the center of the Earth, and then that extra 270,000 meters above the surface of the Earth. So go ahead, pause and see if you can figure that one out. All right, did you come up with this as an answer? Now it should make some sense that this 60 kilogram mass is less than it would be on the surface of the Earth because the distance back to the center is less. And there you go. Yeah, I guess you would have needed to go back for the mass of the Earth and the radius of the Earth. Okay, and as a follow-up question, what is the acceleration due to gravity? Well, this is kind of an old question, right? We've retired the space shuttles, but it's certainly good as a practical problem for us to do. And, ooh, there goes the space shuttle darting around. The answer that I got was 9.02 meters per second squared. And hopefully that works out for you. All right, and if not, of course, you'll bring your questions back to class. All right. Okay, so here's another one. We have to talk about the idea of centripetal force. It is the force of gravity that keeps the planets going in nearly a circle. And for our calculations of these types, we'll assume that the Earth is going in a circle to start with anyway, even though that's not exactly true. Okay, so gravity is creating centripetal force. We know that there's always got to be some force that supplies that centripetal force. And for planets and satellites, it's gravity that does that. Any object in order has a centripetal force due to gravity. All right, so let's see. We can talk about gravitational attraction using this equation, and we also talk about centripetal force with this equation you'll remember from our discussion of circular motion. These two forces are equal to each other, so now we can find out some pretty interesting things. Let's try it, see what we can do here. Right? Okay. So we know this and we know this, that these two things are equal. And that means we can start taking out some of the masses. We can reduce it down. So here, if we use m as the mass in the center of the orbit, because it's its mass that's causing the centripetal force, all that gravity there, then we've got a nice equation for figuring out orbital velocity. Anything faster than this and the object will go out of orbit. Anything slower than this and the object will come crashing back to the planet or the moon or whatever it's orbiting around. Okay, so let's see. Oh, here I do give you those values again. There's the mass of the Earth and the radius of the Earth. And the question here is about the orbital velocity of a satellite. Well, this is pretty important to figure out how fast your satellite should be moving. Actually, probably they'll be hooking up a series of satellites, and there's so many of them up there. You know, sometimes when people say to you, hey, this isn't rocket science. Well, this is. It is rocket science. All right, so let's see. What is the orbital velocity? Maybe you want to pause and see if we got the same answer. Come back and we'll see how we did. All right, here's the answer that I ended up with. Hopefully you got the same thing. If not, we can certainly discuss it when we get back together in class. All right, so here's another one for you to try, and this time I'd like to know how long in Earth years is a year on Saturn. This will take a little bit of thinking, but give it a shot and see how you can do. Pause and come back and I'll give you the answer. All right, well, welcome back. The answer here, well, I guess I gave it to you in stages. First, we'd want to figure out the orbital velocity, and using that, we could figure out the period. That'll come out in seconds, and then we can figure out how many years that would be. So 29.6 years, and that sure is a bunch of years. All right, so I have a couple of questions for you with centripetal force and friction, and we will get back to those questions after a break.